This metamorphic petrology lecture will focus on thermobarometry and pressure-temperature time paths. How do we make inferences about tectonic processes from examination of relationships between minerals and even variations within individual crystals? Understanding pressure-temperature conditions is key to understanding tectonic processes, like the interplay between tectonics and erosion in mountain building, the release of volatiles in subduction zones, and therefore the origin of arc volcanism, or the role of fluids in crustal processes. We have already looked at several qualitative estimates of pressure-temperature conditions of metamorphism. For example, the metamorphic facies concept allows us to match mineral assemblages with regions of pressure-temperature space, bounded by reactions marking the appearance or breakdown of different minerals. For example, we can infer that a glaucophane schist, or blue schist, formed under high pressure over temperature conditions, consistent with the subduction of cold oceanic crust in subduction zones. Some mineral assemblages, particularly in metapelites, provide tighter constraints, as they are bounded by discontinuous reactions over a relatively narrow temperature range. For example, garnet and chlorite appears with a tie-line flip due to the reaction of chloritoid and biotite to form garnet and chlorite. But at just 50 degrees Celsius hotter, garnet and chlorite are no longer stable together and react to form starlite and biotite. However, not all rocks have a suitable bulk composition to produce index minerals, and some assemblages may not provide enough information about pressure and temperature to inform models of the geologic processes of interest. For example, qualitative methods often don't necessarily provide information about both pressure and temperature. In addition, qualitative techniques in some cases give only a minimum pressure or temperature. For example, the presence of a high temperature index mineral may not tell you whether the rock formed at 700 degrees Celsius or 1000 degrees Celsius. And the occurrence of eclogite facies minerals may not tell you whether the rock formed at a depth of 50 kilometers or 75 kilometers. This degree of uncertainty makes the interpretation of metamorphic and tectonic processes difficult. In contrast, thermobarometry allows us to calculate the temperature and pressure of equilibration of mineral assemblages from the distribution of elements between coexisting phases. Continuous reactions produce systematic variations in the composition of coexisting solid solution phases with changes in temperature or pressure. Reactions that are sensitive to temperature make good geothermometers, while reactions sensitive to pressure make good geobarometers. Geothermometers are sensitive to temperature but don't depend much on pressure. For example, exchange reactions involve the exchange of cations with similar sizes and charges between two minerals. These reactions are not pressure sensitive because no major change in volume is involved in the exchange. But they are very temperature sensitive, as higher temperature permits more random, that is, even, distribution of exchangeable cations between phases. The most common exchange thermometers involve exchange of iron and magnesium between two minerals, for example, garnet and biotite. We have previously noted that the composition of solid solution phases change as we examine compatibility diagrams for different pressure-temperature conditions, but we have not examined the sense of change. Here we see that at a temperature of 500 degrees Celsius, the molar magnesium to iron ratio is much higher in biotite than in garnet, while at 800 degrees Celsius, biotite still has a higher magnesium to iron ratio, but the difference is much less pronounced. This distribution of magnesium and iron between phases can be quantified by the distribution coefficient, Kd. At higher temperatures, greater thermal vibration in the crystal lattices make the minerals less selective about the size of ions that occupy the sites, and the distribution becomes more even. That is, Kd becomes closer to 1. By combining experimental data with fundamental thermodynamic equations, the dependence of Kd on temperature and pressure can be calculated, and lines of constant Kd can be plotted. Note the steep slope on the pressure-temperature plot, indicating the reaction is sensitive to temperature but not pressure. This allows us to compare the Kd values in natural rocks, determined by microprobe analyses of the compositions of coexisting garnets and biotites, to the calibrated garnet biotite geothermometer to determine a temperature of equilibration. While good thermometers have steep slopes on a pressure-temperature plot, good barometers have shallow slopes and are sensitive to pressure rather than temperature. Pressure-sensitive reactions involve a significant volume change, such as the transformation of anorthite, calcium plagioclase, to grossular, calcium garnet, plus kyanite plus quartz. This barometer is called the GASP, garnet aluminosilicate silica plagioclase barometer. If we were just looking at the breakdown of pure end-member anorthite to form pure end-member grossular garnet, this would not be a very useful tool, as this reaction is a discontinuous reaction that occurs along a single curve in PT space. However, what the gas barometer is looking at is the breakdown of the anorthite component in plagioclase solid solution, and net transfer of that material to a grossular component in a garnet solid solution, along with an aluminosilicate and quartz, which are not solid solutions. So what do we measure here that can be related to pressure and temperature by the laws of thermodynamics? Recall from your general chemistry classes that for a reaction between substances in solution, the equilibrium constant K is the product of the concentration of each of the products raised to the power of their coefficient in the balanced reaction, divided by the product of the concentration of each of the reactants, each raised to the power of their coefficients. In the GASP reaction, anorthite and grossular are substances in solutions of plagioclase and garnet, respectively. So we could similarly write an expression for the equilibrium constant for the GASP reaction, relating the concentration of grossular and garnet times the concentration of kyanite and quartz, which are both, of course, 1, and the concentration of anorthite in plagioclase, with slight adjustments for non-ideal behavior. This gives us a thermodynamically important variable in terms of something we can actually measure directly in samples. Again, by combining experimental data with fundamental thermodynamic equations, the variation of the equilibrium constant K with temperature and pressure can be calculated, and curves of constant K can be plotted. Note the relatively shallow slope in the pressure-temperature plot, indicating the reaction is more sensitive to pressure than temperature. This allows us to compare the K values calculated from microprobe analysis of the compositions of coexisting garnet and plagioclase in natural rocks to the calibrated GASP geobarometer to calculate the pressure of equilibration, provided we also have a good estimate of the temperature, presumably from a geothermometer like the garnet biotite thermometer or any other geothermometer appropriate for the mineral assemblage present. By applying a geothermometer and a geobarometer together, we can get an estimate of the temperature and pressure at which our stable assemblage of coexisting phases equilibrated. Calculating equilibrium constants and solving the thermometer and barometer equations by hand is kind of fun, but modern computer programs and spreadsheets can offer a better alternative. Computer programs are able to take large datasets of measured mineral compositions as input and utilize internally consistent thermodynamic databases constructed from many experimentally calibrated reactions and solve for the intersection of all relevant reactions involving the stable mineral assemblage, employing sophisticated models for equilibrium constants and propagating uncertainties. Some researchers, like Powell and Holland, have proposed that thermobarometry may best be practiced using a pseudo-section approach, in which a particular whole rock bulk composition is defined and reactions delimit a certain pressure-temperature range of equilibration for the mineral assemblage present. A pseudo-section diagram is made up of regions of pressure-temperature space in which particular mineral assemblages are stable for the given bulk composition. These areas can be quite small, which means that fairly precise estimates of pressure-temperature conditions of peak metamorphism can sometimes be made. In the example shown here, the peak metamorphic mineral assemblage of garnet plus muscovite plus biotite plus sillimanite plus quartz plus plagioclase plus fluid is highlighted in yellow and is considerably smaller than the uncertainty ellipse, shown in gray, determined by the intersection of geothermometers and geobarometers based on compositions of coexisting minerals. Calculated compositions of solid solution phases at different pressure and temperature can be contoured within the region of the stable assemblage and can further constrain pressure and temperature when compared to observed mineral compositions. You may be a little unclear about how a PT pseudosection is different from a petrogenetic grid. Don't they both show changes in mineral assemblages in pressure-temperature space? A petrogenetic grid shows all the reactions that will occur in a model system, for example, calcium, magnesium, silica, water system. However, some bulk compositions will not see some of those reactions. A pseudosection shows fields of different stable phase assemblages for a fixed bulk rock composition. Pseudosections aren't affected by reactions that aren't seen by the chosen bulk composition, so pseudosections are generally simpler and much easier to interpret than standard phase diagrams that show many reactions. Another reason why standard phase diagrams and petrogenetic grids differ from pseudosections is that a petrogenetic grid does not include continuous reactions, only discontinuous ones, i.e. where tie lines are broken and new tie lines form on a compatibility diagram. However, as a field sweeps across a ternary diagram, new phases may be introduced into or removed from a rock with a particular bulk composition, even though no discontinuous reactions have occurred. These changes in mineralogy are explicitly shown in a pseudosection and not at all on a petrogenetic grid. Not only is the pseudosection easier to read, it gives us more relevant information about the pressure-temperature conditions under which an observed mineral assemblage is stable. However, it is important to bear in mind that a pseudosection is only applicable for the specific bulk composition of the sample for which it was constructed. We've now seen several methods of determining the pressure and temperature at which coexisting minerals formed during metamorphism. This already gives us some insights into the environment in which peak metamorphism occurred. But to answer questions about tectonic processes, we need to understand how pressure and temperature vary through space and time. The complete set of temperature-pressure conditions that a rock may experience during a metamorphic cycle, from burial to metamorphism to uplift and erosion, is called a pressure-temperature time path, or PTT path. The trajectory and shape of the PT path, the rates of metamorphic processes, and the duration of metamorphism are a function of the source of heat and the mechanisms of burial and unroofing. Therefore, the shape of the path, combined with time information, provides information about the driving forces of metamorphism. The clockwise loop shown in this schematic PT path is common for regional metamorphism. For some rocks, the only part of the PT path recorded in the mineral assemblage and texture of the rock is the peak of metamorphism, the conditions of the thermal maximum. Other rocks may record more of their PT paths, allowing PT path segments to be inferred from mineral inclusions, element zoning within minerals, and reaction textures. Mineral inclusions within larger porphyroblasts can preserve mineralogical evidence of an earlier stage in the metamorphic history of the rock. For example, kyanite inclusions in garnet in a rock that has only sillimanite in the matrix indicate that the rock was previously in the kyanite stability field, but that PT conditions changed. In addition, the composition of inclusions may be used in thermobarometry to determine pressure-temperature conditions along the path. For example, by applying the garnet biotite geothermometer and the GASP geobarometer to coexisting mineral inclusions and to coexisting minerals in the matrix, you could calculate pressure-temperature conditions at an earlier point in the pressure-temperature path, as well as at peak metamorphism. Metamorphic minerals may change composition in response to changing chemical and physical conditions. When compositions acquired early in the mineral's growth history are preserved during later stages of growth at different conditions, crystals may be compositionally zoned from core to rim. In some cases, it may be possible to apply thermobarometry to compositionally zoned crystals to extract pressure-temperature conditions along a portion of the PTT path during which the crystals grew. Some metamorphic rocks contain evidence for incomplete reactions or other textural evidence for parts of the PT path. Textural evidence may be useful in cases where the reactants have been completely consumed if the shape of one or more reactants are preserved as pseudomorphs. For example, a pseudomorph of chlorite after garnet. An example of a more complex reaction texture involves the formation of coronas, which consist of one or more shells or reaction rims of a mineral or minerals around a central reactant phase. A schematic possible pressure-temperature path illustrates how pressure-temperature conditions experienced by a rock may evolve during burial, orogenesis, and exhumation, and how information about that PT path can be preserved during metamorphism. The mineral assemblage that is likely to be preserved is developed near the maximum temperature. Zone porphyroblasts and mineral inclusions may preserve a record of conditions prior to peak temperatures, and retrograde minerals may develop as rims on the high-temperature minerals during early stages of cooling. Information about pressure-temperature conditions during exhumation may be preserved by fluid inclusions trapped in minerals while temperatures are still hot enough to heal fractures in mineral grains. It should be noted that pressure-temperature paths record the history of pressure-temperature conditions that a rock experienced, and is not the same thing as a steady-state geotherm, that is, the normal increase in temperature with depth into the earth. Nor are pressure-temperature paths the same thing as a metamorphic field gradient, that is, the pressure-temperature conditions associated with a prograde series of metamorphic zones or facies across a region. To understand how pressure-temperature paths are related to geothermal gradients and metamorphic field gradients, consider the pressure-temperature paths of rocks within the same region buried to different depths during an orogenic event. This diagram shows three rocks buried to different depths. The pressure, temperature, time path of each is shown by dashed arrowed lines. Notice that the PT paths during burial lie beneath the steady-state continental geotherm. During crustal thickening, pressure increases basically instantaneously, much more rapidly than temperature because of the time required for heat conduction. The increased thickness of continental crust rich in radioactive elements increases internal heat flux, and subduction zone magmatism may also provide additional heat to the crust. This results in temperatures higher than the steady-state geotherm prior to orogeny. And temperatures continue to rise in our rock, even as erosion of the thickened crust begins to reduce pressure. Eventually, the rock will have equilibrated to a new steady-state geotherm, or heat input will begin to decrease as the crust begins to thin again, so temperature will no longer increase, marking the maximum temperature and peak metamorphic conditions. From this point, both temperature and pressure will decrease as the rock moves back towards the surface. Notice the fine solid lines in this diagram, joining points of equal age along the three pressure, temperature, time paths. While each of the three rocks followed a PTT path that is similar in shape in this example, they reach their maximum temperatures at different times. The metamorphic field gradient is the line joining the conditions at the temperature maxima of individual rocks now exposed at the surface. While metamorphic field gradients can be diagnostic of different tectonic environments, the sequence of mineralogical changes in a prograde metamorphic sequence in the field cannot be considered to represent the mineralogical changes that individual rocks have progressed through over time. While the clockwise PTT paths discussed so far are common for crustal thickening at convergent margins, paths can be clockwise or counterclockwise, and can also vary in terms of 1. How different the prograde and retrograde segments of the path are, either very similar or very different, and 2. How different the maximum pressure and maximum temperature are from each other. PT path shape by itself does not provide a unique interpretation of tectonic process or metamorphic driving forces. For example, some subduction zone rocks record clockwise paths and some record counterclockwise paths. However, the integration of pressure-temperature path characteristics, time and rate information, structural data, and other petrologic information can provide significant information about metamorphic and tectonic processes. Therefore, although rocks in a particular tectonic environment can follow various paths during burial and exhumation, determining the specific path that a particular exhumed rock followed is important for understanding dynamics of tectonic processes.